Hi, now that we have derived the Schrödinger equation using the characteristic function construct, it's nice to try to derive it from another construct that, as we have said in the previous video, will be the entropy. This is important because the characteristic function derivation did give us a lot of nice results, mainly mathematical results. For instance, the Born-Sommerfeld rules, and also an interesting connection with Feynman's path integrals. And in fact, this connection gives us hints, suggestions about what quantum mechanics is all about. But to investigate this further, we need to introduce in our set of concepts other concepts that are akin to the notion of fluctuations and also stochastic behavior. And this is we begin to do that quest to this kind of behavior using the entropy in this derivation that I will now present to you. Then we have already shown that it's possible to derive the Schrödinger equation using the characteristic function, but it was nice in terms of the interpretation. It was nice because it allowed us to connect our derivation with the Feynman's path integrals. And when trying to understand what Feynman's path integrals are all about, we have said that it seems to be connected to stochastic behavior. But this has to be shown. It's not sufficient to just use Feynman's path integrals as a metaphor. We need to show mathematically that this is indeed the case. And this is why we introduce another derivation, axiomatic too, based now on the notion of entropy that I will now present to you. In fact, the notion of entropy is nice because it is connected to the notion of fluctuations and so stochastic behavior. More important, it will be shown in a future video that this axiomatic derivation is obviously connected to the axiomatic derivation using the characteristic function. I will show that they are mathematically equivalent. So let's begin. First, I will have to use a set of notions that will be akin to the use of entropy. Before that, let's state our axioms. The first axiom will be that the product of the mean square derivations of the momenta and the positions of a physical process calculated at each point of the configuration space. This is very important. This means that we are not considering here the Heisenberg rules. Heisenberg rules are means taking over not only the momentum but over the configuration space too. What we are saying here is a little bit more restrictive. We are saying that fluctuations on phase space at each point of the configuration space are governed by this sort of equality and not inequality. So this is important. I will present the interpretation of this further on, but it is important at this point to understand that this is not the Heisenberg rules, but see, I will show too that from these ones you can recover Heisenberg special relations. So this is the first axioms of ours. Let's see the second. The second is exactly the same that we used before, which is the assumption that the integrated in momentum version of the Liouville equation is valid to understand quantum phenomena. So these are the two axioms that we need to derive the Schrödinger equation, as we will show now. Uh, I will begin to present three simple definitions that will be important for our mathematical derivations to come. The first one is, of course, the notion which was already introduced of the probability density calculated upon configuration space, which is just a marginal distribution function. It's already obvious. The second one is the momentum average calculated at each configuration point. Note that we can, using the definition we have already uh, shown to rho, it's obvious that P, Qt can be written as P F dp over F dp, which is reasonable. In fact, these kind of assumption definitions are very well known from those working with the Liouville equation and its moments. The third definition will be related to the second momentum statistical moment, which is just this result I have just shown. And in fact, these three definitions are just the definition of the statistical momentum moments. Then, with using them, it's easy to show that this expression is related to the fluctuations of the momentum related to the average momentum at each point of the configuration space, which I will write in this way. So this is the way by which we calculate fluctuations in these formulas. So let's begin our demonstration. If we integrate the Liouville equation in terms of P, this is a very well-known result. We just get the continuity equation. We can also multiply the Liouville equation by P and integrate it to have the result just shown, in which there appears the second order statistical moment in momentum and also the average of momentum. We can make some straightforward calculations using this continuity equation here to get this result, which explicitly shows the momentum fluctuations at each configuration point. At this point, we find one of the elements that appears in our axiom, the first axiom. But at, at this point, we have used only the second axiom and no kind of entropy whatsoever. So we must use the first axiom, and we will show that in this process the notion of entropy appears quite naturally. Let's do that. Let's try to calculate the fluctuations of positions at each position in configuration space. That is, we have some system, for instance a particle, that at some point in configuration space can fluctuate around this point Q for some quantity that we call delta Q. And in fact, for different points in configuration space, this fluctuation can be different. This is the content of this expression. And in fact, this is the main point of this derivation because this is the way entropy comes about. We now express, using the notion of Boltzmann entropy, we express our probability density function over configuration space in terms of the entropy. Of course, this is the entropy function defined over each configuration point. Now we may do the following. We may calculate our probability density function not on a point in Q on the configuration space, but at a point Q plus delta Q is likely distant from the point Q. We can then use this expression to develop it up to second order. It's important. We always use this notion of second order expansion. This notion should be now assumed as quite natural if we remember that the Feynman path integral uses these two, despite being in terms of the time, but it's the same thing. And now using this expression, we can calculate. Note that this expression is given in terms of delta Q. These terms here are of course independent of delta Q. So we can use this function to calculate the mean square displacements. This can be done using this formula here, which is just delta Q squared, integral delta Q squared minus the average of delta Q. This is just this term, this is the definition. And if you do so, we get the following result. This can be expressed again using the notion of entropy here, which is just the logarithm of the function s. Excuse me. Here we have to have a whole logarithm of whole. But up to this point, I didn't use the notion of the first axiom. The next step is just to use the axiom, which will connect the fluctuations in delta Q with the fluctuations in delta P. In fact, this is the axiom, the first axiom. And if we use this axiom with this result, we get simply that the fluctuations in delta P in momentum can be written in terms of this, here is correct, in terms of the logarithm and the function itself, the density probability function. This is important. This axiom was crucial for us to write this expression for the mean square the displacement in the momentum. If we don't use this axiom, it's impossible to connect this fluctuation with the fluctuation over p. So it's this axiom is crucial for us to get this expression, and as we will show, this expression gives us the Schrödinger equation. Indeed, if we use the usual expression, which is this one already used in the characteristic function derivation, I will use the smaller s here, not to avoid confusion with the entropy, which is a capital S. So if we assume this expression for psi, we get these two results here quite easily. Then, if we put in the Liouville equation that we have derived, we put this result and make some straightforward calculations, we just get these two equations. This one was already obtained, and the momentum multiplied by the Liouville equation and integrated gives us this second equation. And we have already shown that these two equations can be related directly to the Schrödinger equation if we write psi the way we have just shown in the previous images. So if we have, let's recapitulate a little bit. If we can connect these two fluctuations in this way, it is easy to show by calculating the fluctuation over Q that the fluctuation over P is given by this result. And these allow us to get these two equations, which are equivalent to the Schrödinger equation as we have already shown. This is the way we demonstrate that the Schrödinger equation can be derived from the two axioms that we have used. Since we have used two axioms and one of them is exactly the same as the previous derivation, it's obvious that the first axiom should be related to the first axiom of the previous derivation in some way, and this is what we will show in the next videos. In fact, this will be the way we will relate the characteristic function derivation with this entropy derivation. Let's see that in the next video. Thanks for watching.